This is an introduction to bonding for AP Chemistry and giving you some general concepts. We're assuming you've gone through Unit 1 and have a good concept of the modern view of the atom. So, we're going to use a Bohr model here just to demonstrate the ionic bonding. Electrons are transferred in an ionic bond from metal atoms to nonmetal atoms, and this is how it works. As you can see, sodium has one electron in the high third orbital, and the chloride ion is deficient in its third orbital, and so the electron from the sodium 3 is transferred to the chlorine, and that's a chlorine atom, which is going to turn into a chloride ion. So here we are, very active metal. Sodium loses a valence electron to the highly electronegative atom, chlorine. You now get a positive sodium ion and a negative chloride ion, and there is the result. The sodium cation looks like neon, is highly non-reactive, therefore low energy, and the chloride anion, likewise having a full third energy level, is low energy and highly non-reactive. Formation of ionic bonds, then, always involves an expulsion of energy. It's exothermic, we say. To determine the ionic character of a compound, we can do one of two things. Compounds are ionic if you melt them, and they conduct electricity, as you see here in this diagram. That happens at well over 1,000 degrees Celsius. It's a lot easier just to dissolve them in water and see if they conduct electricity there with a conductivity probe. And if they also, in the solid state, exhibit a high melting point, then you know that they are ionic. Now, Coulomb's law tells us the relationship between energy of interaction and the charges and distance between the charges. And that's the formula. You don't have to memorize that or use it for that matter. It means that the energy is proportional to the product of the two charges, numeric value of the charges, divided by the radius, or divided by the distance. Now, this looks a little different from what you're used to, because we're used to measuring force, which is proportional to the charges divided by r squared. Here are an idea of the sizes of atoms and their ions in picometers, and you can see, for instance, for lithium and sodium, that the metallic ions in kind of a pinkish red are considerably smaller than the atoms of the lithium and sodium. And over on the nonmetal side, you can see that the nonmetallic ions, since they've gained an electron, have a filled outer shell. They are larger than the atoms that they come from. Here is a picture of a sodium chloride crystal lattice, animated, and you can see that since it's NaCl, the sodium ions, which are small and in pink, are much smaller than the chloride, and they fit interstitially between the chloride ions in the crystal. Now, ionic compounds will form solids at room temperature, and they organize in a characteristic crystal lattice of alternating positive and negative ions, and the configuration of the crystal is going to depend on the size, relative size, of the ions. In this case, the sodium ions neatly fit between the chloride ions. Now we're going to look at enthalpy of reaction. This is something you're supposed to study in first year, and we're going to see what happens in order to determine what we call the lattice energy is. because this is something that's sometimes operating on tests. So let's suppose we have a very reactive metal and a very reactive nonmetal. And how do we find the energy that is produced when they react? And specifically, what energy is produced when the two ions in the gaseous phase get together and form the crystal in the solid phase? Well, what do you have to do? Well, first you have to vaporize the metal, that is, turn it into a gas. Then you have to rip off one or more electrons. We'll just look at sodium and chlorine for the example. Well, that takes energy. So these first two things take energy. Then you have to take your nonmetal and turn it into a gas, if it's not a gas already. And then you need to rip, if it's, say, diatomic, like bromine and chlorine and fluorine, you have to rip them apart into the individual atoms. Then you have to throw an electron or two or three into the nonmetallic atom to make it a nonmetallic ion. That gives off energy. And then you combine the metal and nonmetal ions to form the salt crystal, the solid. We'll show you an example with sodium chloride here. And we're going for the total enthalpy of formation. So you take sodium solid, react it with chlorine gas to form a solid sodium chloride. Here are the steps. And here are the measured energies that it takes or gives off. First of all, we vaporize the sodium, 109 to the positive. Then we take the sodium gas and we turn it into an ion. Well, you're pulling an electron away from the nucleus, so that's hard. That's going to be endothermic too. So that requires over 4 times, nearly 5 times as much energy as the vaporization. You have to turn the chlorine gas molecules into chlorine gas atoms, and that's a half of 239, since we only need 1 chlorine for each sodium. Then finally we're going to get some energy back by combining the electron with the chlorine. That's called Electron Affinity, and that's exothermic. And now we've got the ions, the sodium ion and the chloride ion, so we let them run into each other, and we get the solid sodium chloride. So the question is, what is the enthalpy of this formation process? It's going to be the place where we started minus the place where we ended, so this is going to be a negative number, and you can see it after we knock out everything except the two things that are involved in the chemical reaction, the chlorine and the sodium chloride and the sodium also reactant. You add all those up, you get negative 412 kilojoules per mole. That's the enthalpy of reaction formation for sodium chloride. So what forces are operating in a covalent bond? Well, you've got repulsive forces and attractive forces. You've got electron-electron repulsion going on here. We're just looking at 2 helium atoms. And you've got proton-proton repulsion from the nuclear interactions. But you also have electron-to-nucleus attractive forces going on. And they have to balance each other out. If you want to form a molecule, the total forces have to be attractive. 1, 2, 3, 4 attractive forces have to overcome any repulsive forces that you see. Now, let's suppose we're putting 2 hydrogen atoms together in a molecule. The hydrogen atoms begin far apart. Enough apart so they have no interaction at all. If they are allowed to come closer together, they begin to interact, and you'll see as we study the formation of covalent bonds that the electron orbitals, originally just plain old 1s orbital, they begin to combine, because that's what a covalent bond is. So they interact, and the energy is reduced as a result, because the attractive forces are greater than the repulsive forces. Now we get here, and you get what's called a bonding orbital. There's another one too we'll talk about later. You get a bonding orbital, you've got the H2 molecule, and the distance between the two nuclei is ideal here. Optimum distance achieves the lowest overall system energy. But if you push them closer together, the repulsive forces are going to increase faster than the attractive forces can keep up. And so now we've got repulsion going on, and thus the atoms will oscillate around the optimum separation distance, which would be what we call the length of the covalent bond. Here's just an idea of the energy of bonds. You can see between carbon and carbon, you've got single, double, and triple bonds. We'll discuss what those are as we go through the unit. And you can see the bond lengths as you go to 1, 2, and 3 bonds between the atoms. The bond lengths in picometers reduce as you increase the number of bonds. You reduce the bond length, and you increase the total bond energy there. Bonds between elements become shorter and stronger as what we call the multiplicity of bonds increases. Here's carbon-oxygen, same thing happens. And here's carbon-nitrogen, which you can also make a triple bond to, as in the cyanide ion. And in each one of these, you shorten the bonds as you increase their multiplicity, and you increase their bond energy. So, more bonds, more bond energy. To determine the bond energy and enthalpy of a formation is you determine what it costs to break up all the bonds in the reactants. And then you always subtract what you gain by forming bonds in the products. Energy required minus energy released gives you the overall enthalpy of the change. Breaking bonds requires energy, it's endothermic. Forming bonds releases energy, exothermic. These are all concepts that you should have learned in first year and in biology. So let's do one. Calculate the delta H of reaction of methane. We start off with methane and oxygen. So we're going to burn it, combust it, and we have to break up some bonds into atoms. Now this may or may not happen in actual mechanics of it, but this is the energy we're trying to look at. Now we've got these, and we can reassemble these atoms. So we've broken bonds to get to the atoms, and that cost us 2,648 kilojoules per mole. Now, go to the products. And this is the total energy, delta H, of the products. We form new bonds, and that's going to give us back 3,466 kilojoules per mole. Now the net, then, is for you to calculate. Remember, it's bonds broken, delta H, minus bonds formed. So you're going up here, you're going down here. And you're actually going to add these two numbers, 2648 plus, and then you subtract 3466, and of course that's going to give you a negative number in the vicinity of 1,000 kilojoules per mole. After we have finished this, we'll have part 2 of our bonding presentation.